we're going to learn about the nearest neighbor algorithm. This algorithm is a greedy algorithm, and basically it determines the shortest path to all vertices given a graph. It's known to solve the traveling salesperson problem, which is given a list of cities and distances between any pair of cities. What's the shortest possible route that visits each city exactly once and then returns back to the original city. It does usually solve the traveling salesperson problem pretty well, but that doesn't necessarily mean that it will always give us the most optimal solution. So I'm going to do two examples. I've got down here path 1, so we're just going to pick a starting point, which is A. We're going to go through the algorithm and find the shortest path. So starting at A, the vertices given, which is the shortest path? So I've got A to F is 34, A to E is 49, A to D is 57, A to C is 37, A to B is 58. So this is our smallest one. We're going to pick that. Same question, smallest weighted edge of the ones that have not been visited, of the vertices. In this case will be D. Same question of the unvisited vertices. We got E. We're left with C and B with weights of 48 and 53. 48 is smaller. B is our last vertex needed to be visited. And then remember, we got to get back to the original city. Okay, so our first path was A, F, D, E. Then we went to C, to B, and back to A. We're going to find the weight of this too. This is going to be 195, and that's just adding up all the edges weights. Okay, let me go through another example. I'm going to do green for path 2. We're going to start at D this time. My colors are going to overlap, but that's okay. Alright, starting at D, my shortest edge is to E, got 6. Then I've got F, which is 24. Then after that, F5 would go back to D, so we can't hit that one. We'd have to go to A. We got C and B left again, which it looks like is 58 and 37, so we'll take 37. B is our only unvisited vertex, and then we have to go back to our original city. So for this one we did D, E, F, A, C, B, D, which if we were to add up all the weights for this one, we get 162. So notice that your starting vertex changes your total weight by a lot. Like we went down 30 just from starting at A to starting at D. So the time complexity of this is mainly based on your input and the size of your graph and vertices that you're given. The time complexity usually averages about big O of log n. Some implementations would be linear search, which computes the distance from a given point to every other point and finds the shortest distance. So in our example, that would be our edge weights. It also goes with space partitioning. It's just another method of implementation. It partitions the data set into 2 separate groups and then applies that naive approach on one side at a time. So this allows for like the potential path to be found in the first partition and the other one not needing to be ran because you found it in the first partition. So this could possibly cut down on time complexity. People implement this to do pattern recognition or statistical classification or databases, plagiarism detection, tons of other stuff that's just pattern recognition type problems. It has tons of variants, nearest neighbor, approximate nearest neighbor, all of these nearest neighbor algorithms. They basically do the same job. They go about it a little bit different way, averaging logarithmic runtime and usually the size of the input for space complexity.